where they actually want your cell phone data.
Apple does that. Apple does that.
Yeah, I know, but there are employers that require that you have you wear a Fitbit so that you make sure that you're keeping their insurance costs low.
Keeping you healthy for a long
That's right. Nothing is pure except math. Anyway, so today
several times that it isn't.
I watched the video on what is it, like set theory or something? That doesn't make sense.
Set theory?
Yeah, the sets that have a set.
Oh,
yeah.
Russell. So you're talking Russell's paradox. Yeah. Does the set of all sets include itself? Yeah. There you go. The answer is that problem is so bad that they had to redesign the way math worked to make sure nobody could even ask that question. So.
You're telling me that's pure.
Yeah.
It is. I mean, it was a great disappointment to the mathematicians of the late 1800s that math was full of internal contradictions, and so they just took the internal contradictions and they defined them away and said, okay, well, we're just not going to allow you to ask that question. So you're not allowed to ask if the set of all sets contains itself.
That's a little stupid.
Oh, I mean, Russell was not happy about it, or like all these like really famous people that built this program. No, they weren't happy about it. And then it turns out that there's an even weirder theorem called Gödel's theorem. You guys really want to go see something brain breaking? Look at Gödel's theorem. Gödel's theorem says that every mathematical system complicated enough to include the integers inside of it is either internally inconsistent or contains things that can't be proved. Either there's statements you can write down that have no proof right or wrong, or there are statements that are true simultaneously that contradict each other. So this is like, if you don't understand that, don't worry about it. Just go look at this, and then you'll also not understand it because nobody really does. I'm not sure he did either. He was friends with Einstein. He walk around Princeton and talk about this stuff. Okay, so today we are not talking about Gödel's theorem. We're talking about parametric equations. Let me remind you where we're at. Are there any questions I can answer before we get started? No. All right. Let's do, here's a reminder of what we know so far. So we studied functions that look like R is equal to f of theta, where the idea here was that theta is equal to an angle, and we're thinking about this as an independent variable. And R is the radius. Thinking about this as the dependent variable in the function. And we have these transformation equations that we can use to get into and out of polar equations. So anybody who has done free body diagrams in physics has seen these before, where you can decompose force, directions, components, and on the other hand, so this is the formula that gets you from radius and angle to x and y. You can go the other direction. Tangent of theta. You should know these transformations. It's life a lot easier. Okay, and I think these are worked pretty extensively in the homework to use these. Okay, what else did we learn last time? We graphed some stuff. So we graphed stuff like say R is equal to cosine of theta. I'm not going to redo that, but when you did that, I think you ended up with a circle. Like that. Imagine that dot right there at the origin. And the way that we did it is we thought of taking an angle theta, say of pi over 4, and producing a radius. And we went out in that direction, and along the ray that we produced with the angle pi over 4, we rotated up to that from theta is equal to 0 axis. The length, the distance that we went from the origin to where we drew the dot is the radius. That's why we're thinking about it as a radius. So this angle was pi over 4. This distance is root 2 over 2. And so that point right there is the point located at pi over 4, root 2 over 2. And then if you do that for enough dots, you get this circle off the other side. So I'm going to start today with an example of a function, a slightly more complicated function that, yes, turns out to be called a cardioid for Valentine's Day. It's not on purpose. So let's plot y is equal to, not y, r is equal to 1 plus the cosine of theta. Just so that we get away from the idea that everything in polar coordinates is circles. Okay? And also, I want you to be really careful about, you have 4 or 5 or 6 years of math screaming in your brain right now, telling you that this is a shifted function because it's cosine of theta, but then you've shifted it somehow. Except it's not, because this is a shift in radius. It doesn't change the center of where we're rotating. We're always rotating with respect to the origin. This is not a shift in the way that we're used to. So you have to be careful with these. Okay? So I'm going to do a sort of detailed plot of the first quadrant and then a less detailed plot of the rest of them so we can see what this does. I will tell you that these functions are some of the primary examples that get used in the study of polar functions and getting used to how they work. So I'm just going to do all of them here. 0, pi over 6, pi over 4, pi over 3, pi over 2. Every sort of unit circle first quadrant angle. I'm going to again ask for your own sake that if you're looking at a simple trigonometric equation like this, that you can think about applying this equation to these angles quickly enough that you wouldn't even really have to write these down to do it. It's not required, but it's going to make your life a lot easier if you can look at 1 plus the cosine of 0 and just immediately write down 2. Or 1 plus the cosine of pi over 6, which is 1 plus root 3 over 2. And you should have in your head, again, you don't need it, but it is nice to have when you're working with no calculator. Root 3 over 2 is about equal to 1.7 over 2, which is about equal to 0.8. So I would call this about equal to 1.8, just for the purposes of plotting. It's nice to have quick approximations for these guys. 1 plus cosine of pi over 4. Notice it's not even a terribly accurate approximation because it's closer to 0.185, but who cares, right? 1 over 4, 1 plus root 2 over 2. So root 2 over 2 is about 0.7. Root 2 is about 1.4. Divide by 2, you get 0.7. This is about equal to 1.7. This one I suspect everyone knows. 1 plus 1/2 is about equal to 1.5. Yeah, plus or minus 0, right? That's how close it is. And 1 plus the cosine of pi over 2 is the same as 1 plus 0, which is about equal to 1. Okay, so let's just look at the first quadrant points here so we get an idea of what the beginning of this graph looks like. And then we'll be a little less stringent about the points in the remaining quadrants. So one strategy for plotting polar graphs, especially if you don't have polar graph paper given to you, is to give yourself some polar graph paper. So give yourself the hash marks on the axes, and then draw the circles that go through those points. It doesn't have to be totally accurate, but it's going to make your graphs nicer if you have some way of estimating the radius in a consistent way as you draw. So what does this say to do? It says in the theta equals 0 direction, go out 2 units. And in the theta is equal to pi over 6 direction, go out 1.8 units. And in the pi over 4 direction, go out 1.7 units. And in the pi over 3 direction, go out 1.5 units. And in the pi over 2 direction, go out 1 unit. So the reason that, the polar graph paper just makes it easier to get these dots arranged sensibly. Does this make sense, by the way? Have I lost anybody? Remember that what we're measuring for any given angle is the distance from the origin, right? So at this angle, I went out 2 units. At this angle, I went out 1.8, 1.7, 1.5, and 1, as I rotate up. When you connect these guys, you get something that looks like this. If we want to throw some more points on the graph, just to get an idea of what happens on the other side, let's just look at 3 pi over 4 and pi. At 3 pi over 4, you get 1 minus root 2 over 2, which is about equal to 0.3. And at pi, you get 1 minus 1, which is 0. So at this angle, you're all the way down here at 0.3. And by the time you come out to the angle pi, you're back at the origin. And so what you end up with is a figure that looks like this. And if you go the other way, so there's symmetry here because of the cosine. I did not do this on purpose, I promise. Do I seem like the sort of person that would do this on? I might do it on purpose, ironically. Anyway, so this is called a cardioid. Or heart-like. The idea here is that this gives us a basic family of functions we can work with that aren't circles. And when we're working with non-circle type objects, we can do calculus with them. It's like when you upgrade to quadratics from lines, and you get things that the calculus is more interesting on parabolas than it is on lines. Okay. So one question that might occur to you is, how many points do you actually need to draw one of these things accurately? Because if you did all the points all the way around the unit circle, that's a lot of points to draw, right? And the answer is the sort of the math professor's answer, which is you draw as many points as you need to figure out what the shape of the graph is. Like there's no way I can give you a guide. I would say that for me, since I knew this was going to be a cardioid, I would have just done this point and this one and this one, and I would use symmetry to reflect it. For you guys, you actually might want to know at least the pi over 4 angles. But if you're not confident, draw more points. Especially in a quiz or exam type environment, it costs you like 30 seconds to put another dot on the graph to make sure you not give me some kind of like, you know, these dudes that I see all the time. I have seen everything I draw on the board that I tell you to avoid. I have seen people turn it on exam. I don't know if people working on exams are working ironically, but if they are, that's pretty great. All right, so this is representative of a larger family of functions that I want to at least point out exist because they're so commonly used in the study of polar functions. So I also want to show you guys the rest of the family. So you have things that look like R is equal to A plus B cosine theta, or you could put a sine theta here instead and they just rotate up. You can also look at R is equal to A plus B sine theta. And if A is equal to B, then you get the shape that we just drew. The reason is that what happens is the positive direction from the A and the negative direction from the B cancel each other out into a 0. That's why you get this. Okay. If it turns out to be the case that the A is bigger than B, then you never quite get back to the origin, and you get things that look like this. Kidney bean looking things. Right? Kidney bean is less romantic than a cardioid, I guess, right? These are usually called limaçons. French mathematicians. And finally, my favorite of the pile, the lemniscates, which means snail-like. So if you go the other direction and A is smaller than B, then you end up with shapes that loop back around on themselves like that. It's called a lemniscate. Remember in the 16 or 1700s, you would have been pretty excited to draw something like this down. No calculator, right? So you have to study the families of functions you have access to, and this is one of those families. So it's very likely that you're going to be asked to plot or work with all of the things in this family of functions. So there's another family. And that's what I'm going to use to motivate the next part of the class where we move, well, actually not, we're not going to do that yet. First, we're going to talk about the next obvious question is, we have this family of functions and we want to do calculus to it. The first move that we make is think, okay, the basic question of calculus is, what is a tangent line to this graph? Right? So you say, oh, well, how can I find this? It looks like it's got a tangent line. The equation of that tangent line, and this is where the unfortunate thing is going to happen. The equation of that tangent line should be y minus y naught is equal to m times x minus x naught. If that tangent line exists, it has this equation in terms of x and y, right? Where the m is given by dy dx. So I better have some expression I can use for dy dx. Unfortunately, I'm working with radius and angle. And changing from radius and angle to x and y in the derivative is kind of nasty. I'd ask why? Why would it be so much worse than just doing dy dx? And what I want you to think about is, what does derivative mean? If I wrote down dr d theta, what do I mean? Because the first thing you might think is, oh, well, it's just dr d theta. Boy, it would be nice if that was the case. What is this? What does this measure? So I got some little change in theta. I wiggle theta just a little bit. What am I measuring with this? How badly the radius changed, right? So this is called an angular derivative. Because it tells you how fast the radius changes as the angle does. If you're on a circle, this is constant. So the objects that have constant angular derivative are circles because the radius never changes on a circle. It's always constant. So on a circle, this is 0. This is the change in radius with respect to change in angle. And oh, that's unfortunate because it means that if I want to know change in y with respect to x, I'm going to have to reverse engineer the fact that I'm studying angle and radius instead. So it's not just a simple substitution. I have to go one step further than that. And we're going to have to use the math that we already know about parametric equations to do it. Okay, so again, I want to emphasize here, in an angular regime, what we're studying is how things change as the angle moves from a fixed point. In an x and y setting, we're trying to study what happens to the curve as we slide along the x, what happens to the y value, which is a completely different way of thinking about the geometry of the picture. So you should expect this formula is going to be a little gnarly, and it is. So here's how we start. Assume that r is a function of theta. It is. For us, our example was r is equal to 1 plus cosine theta. So the function that gave this graph is r is equal to 1 cosine theta. I know that x is equal to r cosine theta, y is equal to r sine theta. But if r is f of theta, then I could replace this with f of theta cosine theta. And y is f of theta sine theta. And notice now, x is just a function of angle. This is the expression that gives me the x coordinate as a function of the angle that I'm at. And this is the expression that gives me y as a function of the angle that I'm at. So what this is saying is, this is x and y as a parametric function of theta. So now I've got x in terms of nothing but thetas and y in terms of nothing but thetas. So that's just a parametric function. We did this with t's before, but instead of t, I'm using theta now. So I've got a question. Since it was a week ago, maybe people already forgot. If I wrote down x is equal to f of t, y is equal to g of t, and I ask you to write down dy dx, what did you write? y dt over dx dt. If instead I wrote down x is equal to f of theta cosine theta, y is equal to f of theta sine theta, and I say find dy dx, what do I write? I mean, I haven't changed anything, right? It's just, this has t's, this is a function of t, and this is a function of theta. Unfortunately, the derivative here was f prime. The derivative here is going to require a product rule because these cosines and sines are running around as well. Does that make sense? So dy dx, I have to use the product rule to compute. dy d theta is a product rule, dx d theta is a product rule, and so dy dx is going to be a fraction that has all kinds of product rule stuff running around inside of it. Now again, the reason that happens is we're moving from a situation where we're studying how things change with respect to angle to thinking about moving around this way, which is why the formula is so bad. So we might as well compute it. I'm still debating with myself if I want you guys to memorize this one or not. Let's just write down what it is. If x is equal to f of theta cosine theta, then what is dx d theta? F prime cosine theta minus f of theta sine theta. Is that okay by the product rule? Derivative of the first part times the second plus the first part times the derivative of the second. That's where the negative sign comes from. Derivative of cosine is minus the sine. Okay? Now, I can rename this so I'm consistent about using Leibniz notation. The book likes to do this. It just calls this dr d theta, and it calls this r. So I just substitute f of theta back for r and f prime of theta for dr d theta. That's what it calls. This is only notation. All right. There's dx d theta. Y d theta is going to be, well, let's write down y first. F of theta sine theta. So by the product rule, dy theta should be derivative of the first part times the second plus the first part times the derivative of the second. And again, it does the same substitution where it says, well, f prime is really just dr d theta when you compute it. F, that was just r. So there's dx d theta, there's dy d theta. So if I want the derivative, just divide. Dy dx is dy d theta over dx d theta is dr d theta sine theta plus r cosine theta divided by dr d theta cosine theta minus r sine theta. That's the best you can do. Yeah. This tells you something about the difficulty of moving back and forth between square coordinates and angular coordinates, right? That this transformation from angular to square is hard. Yep.
Do you have to integrate that back to x?
No. No. Possible. Yeah, we're going to study. We're going to by the time end of the class today, at least we're going to indicate what's going on with polar integration. We're not going to really do polar integration today. We're going to point to what happens when we start talking about polar integration. So yes, the fundamental theorem of calculus applies to polar equations as well. It's just usually the case that if you get something out like this, it can't be integrated except numerically. And so yeah, most regimes are numerical. That's like kind of the deal. Okay, so for our question, I wanted to know what the slope of the tangent line was here so I could draw this tangent line on the graph, right? And that means I need to know the derivative evaluated at the point at the angle pi over 2. That's pi over 2 in angle. Oh, so I guess I better compute this. It's so depressing. It's not really. Just trig. Okay. Yeah, you notice. Have I even pretended that I'm going to tell you anything about a second derivative here? No. Are we going to touch that? You guys want to know about polar second derivatives? You feel free.
No.
You might not be able to avoid it.
Okay, well, I can avoid it for now.
Aren't you an arrow?
No, I'm computer
Oh,
science.
okay, you're not the arrow, yeah. Just never program 3D graphics, and you never have to worry about it.
Cool.
Okay, so for us, for the equation r is equal to 1 plus cosine of theta, then dy dx is equal to, okay, so it's dr d theta, which is minus the sine of theta, times the sine of theta, plus r, which is 1 plus the cosine of theta, times cosine of theta, divided by dr d theta, which was minus the sine of theta, times the cosine of theta, minus r, which is 1 plus the cosine of theta, times sine theta. All this is literally just this formula right here, but with dr d theta and r. That's all it is. So my question, this is that. So what am I contemplating here?
Oh man.
I am contemplating if I actually want you to know this equation or not. And my gut feeling is no, that if I want you to do this, I'm going to give it to you because it's kind of esoteric. It's useful, but like if you were using this in real life, and you would never actually have to have that in your head. There's other things I want you to memorize. So if I think the deal is if I want you to use this, I'm just going to give it to you.
So I know how you do it.
Okay. I would be doing you a huge disservice if I mean the best I can do with the unit circle is I'll tell you what I'll give you for a unit circle. We'll make a deal, except I get to say what happens. I'll give you a piece of paper that has this written on it.
Yeah.
There you go. What is a unit circle but a circle of radius 1? So you can have that.
You didn't label the radius.
Okay, so if I was asking you to do this on a test, or not a test, like for me, and I asked you to compute a derivative, this would be good enough. You don't need to simplify this any further for me. And WebAssign would actually be happy to take this in this form as well. If you want to simplify it, you should. It's like a puzzle box where you can look at it and say, oh, well, really secretly, if you look at it closely, the top has a cosine of 2 theta in it. And the bottom has a sine of 2 theta living inside of it. So there's something going on here with some indifference of cosine of 2 theta and sine of 2 theta. You don't see why that happens. This is a cosine squared, and that's a minus the sine squared, which is cosine of 2 theta. And at the bottom, we have sine cosine and another sine cosine, both negative, and they pile up into a 2 cosine theta sine theta, which is the sine of 2 theta. So there's some reduction to be done here, but do I care if you do it? No. I mean, all of you should clearly have all of your trig identities memorized. Well, how have you been spending your time? Enjoying yourselves? Working on homework in other classes? No. You got to open the back of the book. And then that back here somewhere is this insane chart of trig integrals that nobody uses. Maybe it is in the front. I don't know. Wherever it is, you just go there and you sit around all by yourself. I don't know where it is. It's in here somewhere. I'm going to suggest that it's a terrible use of your time to sit around and memorize trig identities. But you should do it anyway because they're fun. Anyway, so I don't care. To be serious, this is not something I want you to algebraically work with. I just want you to write it, right? To write it, know where it comes from, be able to use it. At the point of this. Yeah, and if you wanted to evaluate it at that particular point, you would just do dy dx evaluated at pi over 2. If I gave you a question like this to evaluate, I'm going to give it to you a point where you can just read off what the values are. What is the sine of pi over 2? 1. So we get minus 1 times 1 plus 1 plus 0 times 0 divided by 0 minus 1 times 0. Oh, can that be right? Have I made a mistake somewhere? Oh, no, I got this backwards. It's 1 plus, it's 1 times 1. That's slope 1. Yep.
Would we be able to just leave it as like sine or parametric?
That's making sapping my will to live.
I mean,
That's like when people write this down.
Like, you don't have to write the
Yeah.
answer.
Oh, Ryu says yes.
Rudy.
Oh, why it hurts me. Yeah, I mean the thing is, if I ask you to plot
But
something,
I'm terrible.
look. If I ask you to plot something, and I go out of my way to give you pi over 2 as the point where I want you to plot it, and the result of the entire thing is 1, and you try to plot something where you have this with pi over 2 is written over, are you just going to put this? Is the answer to the question y minus y minus 1 is equal to all of that crap with pi over 2 all over the place? Is that really what you're going to write instead of just a 1, and then you're going to drop a line and pretend like you know that's 1?
Yeah.
I mean, I guess you get credit if you did that, but I mean,
I didn't know this was something.
I just whatever. I try to avoid that that sort of conversation. I mean, it would be to your benefit to plot this just so you have an idea of what the flow factor is. Right? But from a computational standpoint, nobody does this by hand. Everyone does it numerically. So what I want you to do, I want you to know where these things come from and how to use them. I'm not putting a lot of emphasis on hand calculation.
What's your constant?
So the answer to that is get good at your, increase your confidence with your abilities to use the unit circle by way of getting good at using the unit circle. You can't escape it. You can't escape it. You can't. Dude, look. Look. Okay. All you have to do, okay, can you count from 0 to 4?
Yeah.
Okay. Okay.
You hesitated.
I mean, can you do that?
Yeah.
Okay. So here's what I want you to do. At every point, put a 4 in. Every one of these points has a 4 in the bottom. All of them.
It does.
You have no idea what I'm doing because nobody's ever shown me this.
Yeah.
Okay. In the top, put square root at the top of everything.
What?
Okay, now you just have to be able to count. Can you count from 4 to 0?
Oh, it goes backwards.
No
Sorry,
way.
it's not 4. It's 2. I'm wrong. 2.
Really?
Are you
Okay,
kidding
now
me?
4, 3, 2, 1, 0. 4, 3, 2, 1, 0.
Are you kidding me?
Nobody ever showed you that?
No.
4, 3, 2, 1. If you want, you can even put the square root in the bottom and put the 4s down there, so it's only 4s. But yeah, it's literally just count from 4 to 0. That's it.
What?
That's all it is.
It's more impressive than like.
I'm sitting up here finding exotic cardioids and tangent lines. I mean, it's like I'm being a magician or something, right? Like I made the coin disappear. Like, yeah, nobody ever showed you that. Okay. And then if you want to know the rest of it, you just keep counting, right? You go, 4, 3, 2, 1, 0, 1, 2, 3, 4, 3, 2, 1, 0, 1, 2, 3, 4. Like it just goes around. You just have to keep track of what the negative signs are. That's it.
No way.
And oh look, this adds to 4. So if you can count like this, this must be 3, and this must be 2, and 1, and 0. Like easy. Yeah.
Oh my God.
Anyway, that's how the unit circle works. If you do one quadrant, you can do all of it. So why are there no excuses with the unit circle? Anyway.
I was not made aware of this beforehand. The prerequisite.
I mean, the serious take on this is that when I was in school, people took a year of trigonometry. And then most people don't do that anymore. Most people have trigonometry squeezed into some sort of pre-calc and trig class where maybe the teacher spends 2 weeks on trig and it's mostly identities. So, all right. So let's talk about the next big question of calculus. So now what we've got is how to plot one of these graphs, how to convert, a very interesting way of looking at the unit circle, the idea of how to convert derivatives I'm not going to draw it again, whatever. Right, so we know how to compute derivatives. The next obvious question to ask is, how do we compute areas? So I might ask, what is the area contained inside this cardioid? Or more reasonably, there's another family of functions that we study that look like this. So this particular family of functions, like r is equal to cosine of theta, looks like, this is reasonably possible. This comes through and down and over. Oh, I didn't go all the way around. Four-leaf clover. Okay.
Yeah.
So now I haven't drawn this particularly well because these loops don't overlap, right? They come together in a midpoint here. So it really is like 4 non-overlapping loops. And I'm just going to tell you, for the purposes of this motivating question, that one loop of this is contained between the angles of minus pi over 4 and pi over 4. So if you just look between those two angles, you would get a shape that looked like this. Yep.
I have a question. Is this like the chemistry in a way? It's like the orbitals of like electrons. It looks exactly like this.
I don't actually know. I don't think so. I mean, the reason that they look like this is because yeah. They are, it is because the in chemistry where this comes up is in there's solutions to a differential equation that are built in terms of sines and cosines. So yeah.
Oh, chemistry is similar.
Oh, I mean, there is no subject that lies to you more than chemistry.
Don't worry, chemistry is just linear analysis in the background.
Well, it is, but it's also chemistry. I don't know if there's a subject that does more to tell you that there's rules, and then so in each subsequent class you learn that actually the rules don't work at all, and you have to actually learn everything ad hoc and memorize a ton of crap because the rules just don't work.
I hated chemistry.
Yeah, chemistry sucks.
Anyway, hey, we're not here to disparage chemistry. We're here to answer the question: how the hell do I figure out the area contained inside this loop? Because what I'm going to ask you is, compute the area contained in one loop of the function r is equal to the cosine of 2 theta. The problem is, everything we know about how to integrate doesn't work in this setup because integration also requires that we think about rectangles. Now, I'm not going to rehash all of the development of the Riemann integral, but you should at least know what's going on when you write one down. When you write down a Riemann integral, the obvious approach here is we want to use integration. But it may not be easy to turn one of these functions into something with x's and y's. I've never seen a function of x and y do this, ever. There's no function of x and y that will make this happen. Not in any sort of clean way. So we want to use integration. Well, when we integrate, the way that you learned it the first time, when you integrate, you do this, right? You take this area, you cut it up into what? What are you thinking of the area that's being chopped up into?
Rectangle.
Yeah, it's a sort of square, rectangular shaped, right? And what you do is you make the assumption that everything is really a rectangle. You say, oh, well, if these are small enough and the function doesn't go up and down too much, and these things are basically rectangles. And the way that you compute the integral is you say, oh, whatever that area is, it's about equal to the sum of the heights of a bunch of rectangles times the width of a bunch of rectangles. And that's what integration is. Just, I mean, each one of these is a delta x, that's the width. You go up to the top, that's f of x, that gives you the height. And so the area contained in that rectangle is the height times the width, and then you add them all up. And then there's a limit argument that you use to say, oh, well, if the rectangles got skinnier and skinnier until they became infinitesimal, then the area would actually be equal to the integral from a to b of f of x dx, but it's the same thing. You're still just saying the height of a rectangle times the width of a rectangle. Why do we choose the s for integration? Because sigma starts with s for sum, and the integral symbol is also an s for sum. So it's just summing up a bunch of rectangles that are really skinny. Now the problem is that doesn't work here because there's no rectangle. What's moving is not x. What's moving is theta. Theta is the thing that has little tiny movements. So if we want to work in the polar setup, the basic thing that we're trying to break our shape up into looks like this. Little tiny change in angle. So you can think about this change as being delta theta, a little itty bitty change in angle. And if we make a small enough change in angle, we can make the assumption that out here, radius is constant. And if the radius is constant, this looks like a piece of a circle. I asked the last class this, if anybody remembers what this is called. So I'm going to ask you guys the same question. Then I proceeded to get the area formula wrong. But there's a circle-ish. If I put a piece of a circle swept by an angle theta, what is that called? What sector? Sector. This is a circle sector. Does anybody remember how to find the area of it? So do you remember arc length? No.
Yeah.
Oh shit. So R, so the length of this little bit out here, the length of this, L, is equal to R theta. And the area formula is actually related to this. So this is the length of this little arc out here. Now this is actually why we use radians, so that we can just write this formula down without pi over 180 running around inside of it. Okay. So with radians, this is a dead easy formula. It turns out that if you integrate this formula with respect to radius, you get the area for the sector. So the area of a sector is 1/2 R squared theta. This would be a formula that you've seen somewhere in your life before. Yep.
Can you just do pi squared times theta over pi?
You can. But that puts you into, as soon as you're starting to multiply by 2 pi, I mean, yeah, be careful with the 2 pi's. Just be careful with the, be careful. You don't want to convert the radians out of the problem.
Pi over 360, like whatever.
But there's a couple different, don't worry about integrating. Just remember the formula. That's basically the upshot. Just remember the formula here. Okay. So this is the formula that tells you the area of a sector of a circle where the radius is constant. So in the same way over here, we pretended that this function was cut up out of rectangles, even though they really weren't rectangles. We're going to pretend that this shape, when I cut it up, each one of these shapes is basically, if I look small enough, one of these basically looks like the sector of a circle. We're going to say, well, yeah, the radius changes, but not very much. And so we're going to say each one of these can be approximated by 1/2 R squared delta theta. And yeah, the radius is different in each piece, but each one of them has the same form. The area of this piece was 1/2 R squared delta theta for that radius. The area of this one is 1/2 R squared delta theta for that one, and all the way around. And if you want to know the area of the whole thing, you'd say, oh, well, then the area is about equal to the sum of the area of all of these little sectors that we've cut out. 1/2 R squared delta theta. In the same exact way that over here, we cut the shape up into rectangles because it was very natural to think about delta x as the bottom of a rectangle. Over here, we cut this thing into sectors because we're thinking for a small angle, each one of these looks like that. And it works because we're rotating through the area instead of cutting it long ways like this. So then what? Well, there's a rigorous argument to be made here, but in the same way we took the sum of the rectangles and turned it into the integral, we can take the sum of the area of the sectors and just, it's the laziest possible way to do it. You say, oh, well, just take a limit as change in angle goes to 0. And what comes out the other side is the same formula, sum and sum, beginning angle, ending angle, 1/2 R squared d theta. So this integral right here, this is polar area. And it's literally the same idea. you should be able to look at a Riemann integral in the coordinates you're used to and say height times width, add them all up. All that is the sector, is the area of a sector, and you're just rotating through all the angles. Make sense? Okay. Now, why do I keep insisting that you guys remember your double angle formulas? Because this formula has a square in it. Most of the functions we've been dealing with have cosines and sines inside of them, which means these basically naturally give rise to cosine squareds and sine squareds. So let's actually write down what the integral for this problem actually is. Problem says, find the area contained in one loop of this function. We know that one loop of this function, because I told you, is contained between angles of pi over 4 and minus pi over 4. So you would write down the integral from minus pi over 4 to pi over 4 of 1/2 times the radius function, which was cosine of 2 theta, squared d theta. This is already the answer. Not evaluated yet, but this is the area. So, what's that? That is the next thing we're going to talk about, is like why these questions are hard. So that's an excellent question. If I give you the bounds, these problems are dead easy. I gave you the bounds, very easy, right? Minus pi over 4, pi over 4, and then on the inside, you've got this cosine squared of 2 theta. But because you're tired of hearing me talk about it, you went around and you memorized that every single time you're taking an integral of cosine or sine squared, you have to use the identity when you do this. Where did the 4 come from? Well, there was a 2 theta right here. What the double angle formula says is when you do the replacement, you double what was in here. The double of 2 theta is 4 theta. What the identity we actually use here is that, so this is the identity. And I strongly recommend that you remember this one. Cosine squared of theta is 1/2 plus 1/2 times the cosine of 2 theta. And likewise, sine squared theta is 1/2 minus 1/2 of the cosine of 2 theta. These are the integration formulas for cosine and sine squared. You probably learned them the first time as 1 plus cosine of 2 theta over 2, but why put an extra step into your integral? Just learn them this way. Okay. I know probably it's depressing to have to think that like you gotta learn all this trig again, or remember all this trig. You guys all had mastered at some point. Okay, but unfortunately, most things in the world rotate. So a hell of a lot of mathematics and science is built out of the study of how things move in terms of angles. So there's basically no way to avoid it. All right. So from here, once you get to this step, I'm going to call this easy in the sense that this is something you should know how to do. Okay, so the next big question is, what if I didn't tell you what the limits of integration are? What if I just said, the same exact question. Same question, but I don't tell you the limits. So here's an example of what we'll be dealing with next time. R is equal to 3 sine theta. R is equal to 1 plus sine theta. And I say, find the area contained between those curves. So here's the circle. R is equal to 3 sine theta. And inside of it, 1, 2, 3, is this guy. And I'm asking you, tell me what's in there. So you guys remember from calculus 2, I got some people last time grousing that like, oh my God, I thought I could forget calculus 2. This is an area between two functions. There's an outer radius and an inner radius. But the bigger question here, that's actually pretty easy to think about what's happening. This is just outer minus inner. The bigger problem is I don't know where to integrate unless I know where those points are. which means I need to figure out where theta makes both of those functions equal to each other, which means I have to deal with families of equations that look like this. It means we have to talk about how to solve trigonometric equations next time, because every time we're finding intersection points between trigonometric equations, I'm going to have to solve trigonometric equations. Okay, so that's where we're going. We've got the basic idea. We're going to talk about how to find the answers to these equations and how to set up regions contained in multiple curves, right? What's that? This stuff right here, this is kind of like 10 point, the end of 10.3 and beginning of 10.4 all mixed together. Yep. Thank you. Hey guys. Thank you.